So hi, everyone. Thanks for joining us. We're waiting for a couple of minutes so that everyone at Silwood Park can hear us, as it seems that we might have some technical issues there. And we're letting everyone online join. So if you can bear with us for a couple of minutes, then we'll get started with Murray's seminar. Hello, Silwood, can you hear us? This is a test. Perfect. So we can kick off. It seems that all technical issues have been solved. So hi, everyone. Thank you very much for joining this Changing Planet seminar. It's part of our current team, which is Applied Solution for Climate Change. And my name is Arianna, and the seminar series, if you haven't joined us before, it's run by the Changing Planet Science and Solution for a Changing Planet doctoral training program students. And with me, there's Becky here, and Anna is leading things in Silwood Park. The session is recorded, so for anyone online and everyone in the audience, you will get access to the recording of the talk in case you're interested. And if you're online, you can put your questions in the chat. We will have a Q&A at the end of Murray's talk. And as we usually do, we will rotate between different rooms and online to get questions from everyone in the audience. For today, our speaker is Emeritus Professor Murray Moynister, who's joining us from the University of Tel Aviv. Murray has got a PhD from the University of Rochester in 1968, and then he joined the Faculty of Physics at Tel Aviv University, where he carried out a lot of research, especially on high energy particle physics. Since then, and since his retirement, his focus has also moved towards forestry and climate change. And today he's joining us with a talk on the potential global sequestration of atmospheric CO2 by semi-arid forestation. So without taking any further time, I'll leave the floor to Murray, and I hope everything works fine. So you can also put it around your neck. Yeah, sure.
So good afternoon, and thank you very much for the invitation. We've been in London now for a week, enjoying the great weather. So maybe it's a sign that climate is changing for the better. Today, I'll talk about global carbon sequestration in semi-arid forests in Israel. Are we going to have this working? It was working. Okay, so my collaborators for this work are Joel Kronfeld also from Tel Aviv University, from the Department of Geosciences, and Rafat Kubacha, who did his PhD at the Weizmann Institute in Israel and is now a postdoc at Arizona State University. So the work I'm talking about is described in this preprint that we submitted to the archives. And the main points are that we studied the carbon sequestration at the Yatir forest in Israel. It's a 28 square kilometer Aleppo pine forest, and it's growing at the semi-arid timberline. And at Yatir, we measured two things: the organic carbon sequestration and the inorganic carbon sequestration. The organic carbon sequestration rate was measured at 550 grams of CO2 per square meter per year. And if we extrapolate this rate to 20% of the global semi-arid area, assuming that somebody will plant forests in this area and that there's enough water to sustain the forests, then we estimated a global organic sequestration rate of roughly 3 billion tons of CO2 per year. At the same time, we measured at Yatir inorganic carbon sequestration of 22 milligrams of CO2 per liter of soil per year. And this is happens by way of carbon dioxide that is exhaled into the soil by the tree roots. The CO2 is hydrated by soil water. It produces the bicarbonate ion HCO3, and this bicarbonate combines with soil bivalent calcium to precipitate calcite, calcium carbonate. So what we see is we can look as a function of depth. We take a core down to 4.5 or more meters deep, and we look at the concentration of bicarbonate as a function of depth. And we can see that the bicarbonate concentration decreases with depth. And the reason it's decreasing is the calcite precipitates and it's incorporated into the unsaturated zone. So if we extrapolate the rate of Yatir also globally to 20% of the global semi-arid area, which is immense, the global rate, we get roughly 1 billion tons of inorganic carbon. And this is on the assumption that we extrapolate to 20% of the global semi-arid area. So we all know that at the present time, the atmosphere contains 320 billion tons of CO2, and the annual increase recently has been 20 billion tons per year. And we know that excessive carbon dioxide, greenhouse gases, can cause global warming. It can cause climate change, rising sea levels, ocean acidification, ocean deoxygenation, melting ice fields, more forest fires, reduced food supply. So a real Pandora's box of evils. This slide shows the increase of atmospheric carbon dioxide starting from about 320 parts per million, going up now to 420 parts per million, and increasing with time. And you also see on the graph, the blue dots, that the ocean is getting more and more acidic. So this data was taken in the weather station in Aloha, Hawaii. This is a slide from Berkeley Earth, and it shows that the temperature of the planet Earth has been increasing by 1.5 degrees centigrade above the pre-industrial average. The land temperatures has gone up by 2.5 degrees, and the ocean temperature by 1 degree, but the average is about 1.5 degrees. And the sea level has risen since the pre-industrial by 23 centimeters. So all of these are not good signs if you project into the future. If there's a know-nothing activity by governments, then and if we don't get to net zero, then we certainly will have problems. So what can be done? We can burn less fossil fuels, but you need to burn some because you have transportation. You can have nuclear powers, but people oppose it. They're worried about it. But if nobody invests to build safer reactors, then when we really need them, we won't have them available. And the research on nuclear reactors shows that you can now do deep bore drilling and effectively sequester nuclear waste. And that anyway, nuclear power historically has been about 1,000 times safer than coal and oil power. If you count how many people get killed in coal mines and how many people die from particulates in the atmosphere. So it's actually more safe than fossil fuel burning. Okay, you can stop deforestation, but that's easy to say, but not if you live in near the Amazon forest, and that's the only thing you can do is to cut down trees. So there are large, expensive, controversial climate engineering projects proposed for carbon dioxide removal and carbon capture and storage, and solar radiation management, and stratospheric aerosol injection. So this CCS captures carbon dioxide, compresses it for transportation, and then injects it deep for permanent storage. So SAI seeks to reduce global warming by reflecting sunlight using stratospheric sulfite aerosols. So you maybe can do that, but there are some pitfalls in using this kind of technology. So carbon reduction and storage via forestation is lower cost and lower tech and lower risk. So what is carbon capture and storage? You capture it, you transport it, and then you store it. The only one that I'll look at here is item 3. People talk about storing carbon dioxide, but it's actually fake, because it's been used actually by enhanced oil recovery. So there was some huge congressional passage of bills in the USA for carbon capture and storage, and it was supported by the oil lobby. Now, why did they support it? Because they actually had ulterior motives. And the ulterior motives were described very nicely in a New York Times article recently by MIT professor Charles Harvey. He said, carbon, this is more or less a quote, carbon capture and storage is now mainly used globally for the production of oil and natural gas. They pipe captured carbon dioxide for enhanced oil recovery. The CO2 is injected into oil fields to extract additional oil that was otherwise trapped underground. And then the fossil fuel industry needs enhanced oil recovery, so they promote CCS subsidies. So CCS is actually counterproductive waste of money. It masquerades as a climate change solution, while it actually contributes to global warming and slows the transition away from fossil fuels. So it's a waste of money, but it was passed, and it was, and in order to pass it, it had some senators in oil-producing states that supported it as long as they can give the oil companies $100 per ton for storing the CO2, which is not really storing, because you're pumping it down and then you're taking out oil and then you're burning it again. And then when you burn it again, you can capture it again and do the same thing in another oil well. So this is a real fake. Stratospheric aerosol injection. There are proposals to add millions of tons of sulfuric acid to the atmosphere to reflect sunlight, with a fleet of jets working 24/7 to continuously recreate the 1991 Pinatubo volcanic explosion. Now, it's true, after that explosion, for the next year, the temperature dropped. So we can try to make a volcanic explosion 24/7. But the proposed 2 degrees centigrade temperature reduction is not worth the possible deleterious side effects on soil quality, destruction of the atmospheric ozone layer, and increasing ocean acidification. So the Earth maybe will end up somewhat cooler, but at cost of these deleterious side effects: cancer, famine, destruction of oceanic food chain, many possibilities. So here we see the usual smokestacks belching out smoke. And how do we prevent it? Well, we need safer nuclear power. And there are good designs, not like the Chernobyl reactor that was an old-fashioned design that when there's a problem, it blows up. The safer reactors, if there's a problem, it shuts down and automatically with no power. So it's much preferred to CCS and SAI, but it's blocked by many no-nukes who are very nervous about anything that sounds nuclear. Okay, so what about the deforestation? At the moment, the Amazon rainforest is disappearing at a speed of approximately 4,000 football fields per hour. Now, that's a lot of wood being cut down. It's used for, the wood is needed for making fires, for clearing the land so you can make soy farms. And anyway, it gives land to poor farmers who have no other place to live. It gives grazing land for cattle, and you can make roads, you can mine for oil and other minerals. But in the end, there's only so much forest. So if you keep cutting down at this rate, this is what you get. That the amazing thing is that in the Amazon rainforest, there are now droughts. Now, a drought is a lack of water. It should not happen in a rainforest. But the droughts are increasingly frequent in the Amazon rainforest. The trees have openings, the stomata in their leaves. They open and close to regulate the amount of carbon dioxide a tree absorbs and the amount of water vapor it releases. So when there's more carbon dioxide in the atmosphere, the stomata do not need to open so widely, and they therefore release less water vapor, and so that fewer clouds form over the forests. So the Amazon rainforest has suffered severe droughts that killed large amounts of vegetation in the most affected areas. And unfortunately, besides, if the global temperatures increase, then some of the trees will die because they can't live happily in an average temperature that's 2 or 3 degrees higher. So you have all these nice meetings, the COPE climate agreements. There'll be another one in December in Dubai. All the countries, 193 states, they send big delegations to these meetings. It's a real annual picnic, and they make many proposals. And then they're all verbal proposals, and 90% or more of what they promise, they don't carry out. The main aim is to limit the increase of global average temperature to well below 2 degrees centigrade above the pre-industrial levels. But so far the emissions keep rising, and the worst offenders are actually the USA, India, and China, who are responsible for 85% of the global rise. In 2022 and previous COP meetings, the wealthy nations promised to deliver $100 billion per year to the poor countries, and the poor countries are the ones that will be affected by rising sea levels. But they don't. It's just a promise. They don't send the money. So the USA under Trump withdrew from the climate accords. They joined again under Biden, and so far it's mainly all talk and no action. So the wealthy nations do not agree to pay the unpaid $100 billion in pledges. Okay, so let me talk about semi-arid forestation. This is a slide that shows photosynthesis producing and sequestering carbon. So the carbon dioxide plus H2O produces this is a case where the roots exhale CO2. The roots exhale CO2. This is not part of the usual process, but in semi-arid areas, this CO2 combines with soil moisture, and it produces carbonic acid, which decomposes into bicarbonate, and the bicarbonate combines with calcite, and it precipitates calcium carbonate. So the calcium carbonate, when it's precipitated in this way, it's a solid salt, and it stays in the soil long term. Now this works. This process occurs not only in semi-arid, but also in temperate climates. But in temperate climates, there's a lot of rainfall, and the rainfall dissolves these precipitated calcite. But in semi-arid forests, there's not enough rainfall. So once you precipitate the calcite, it stays in the ground long term. Okay, so during the day, the tree produces glucose, carbon dioxide plus H2O. It also has this excellent byproduct of producing oxygen that we need. And the tree, to fulfill its biological function, it uses some of the glucose and oxidizes it to build up the tree, to build up the wood and leaves. And so when it does this biological function, it releases carbon dioxide to the soil in this process. And then when the rainwater percolates down and interacts with the soil gas, it forms the bicarbonate. And this bicarbonate combines with soil calcium. It precipitates the calcite. And so this is a process that works well in semi-arid areas. So this is the usual carbon cycle, and the usual carbon cycle does not have this process of inorganic carbon. So you have carbon coming out of the atmosphere, you have photosynthesis, and then in the end, by decay, it goes back to the atmosphere, and it's a cycle. But this process in semi-arid areas takes the inorganic carbon out of the cycle and puts it away long term. So is there evidence for carbon sequestration? Well, if we look over long times, going back 500 million years in the Devonian period, and then there was even more than 400 parts per million. There was even 7,000 parts per million of carbon, and all of this produced forests, and these forests in the end ended up under the ground and were transformed to coal and oil, and they were stuck in the ground, but now we're burning it and releasing it once again into the atmosphere. So where did we do our study? The Yatir forest is here in Israel. It's north of the Negev desert. It's a semi-arid area. It only gets like 28 centimeters per year of rain. And there are nice rows. It's also a recreational site. It's the world's driest functioning living forest. It was planted over the last 50 years. 4 million trees were planted. It was simply, there was nothing there. When the Ottoman Empire was in charge of the land to run their trains, they cut down whatever trees there were to run the trains. And so we had to start from zero to plant trees, and we're taking the Yatir forest to be representative of how forests work in the whole planet. It would be better if we had data from other semi-arid forests, but at the moment we only have data from Yatir. So this is a slide that shows that there's a lot of semi-arid area all over the globe, 18%. And the only thing that is done with this area now is that it's good for herding and some agriculture. It's hardly used. If you're going to do a forest, you should do it here, because if you do it in a temperate area, then you're taking land away that's needed for agriculture, and it will be needed more, because right now, every year, the population of the earth goes up. So in 20 years, we'll go up past 10 billion, and you need food. So you maybe can use the semi-arid area, but you cannot use the temperate areas. So how did we measure the sequestration rate in the forest? So there were two methods. One is called the carbon stock method. And this method is that we measure the annual net storage of organic carbon in the land biosphere. It's known as net ecosystem production, NEP, and it's the difference between the gross carbon uptake and the carbon loss. And the NEP was estimated at Yatir by carbon stock forestry inventory counting, by keeping track over 15 years. So over 15 years, you measure the diameter of the tree, you measure the height of the tree, and you actually just count. And so that was one method of measurement. And the second measurement is a well-known system. I won't describe it in detail. Wikipedia has a good article about Eddy Covariance towers. The net ecosystem production was estimated at Yatir using an Eddy Covariance tower to measure the soil and canopy emitted CO2 gas over a period of 15 years. And this EC meteorological system measured the exchange of CO2 between Yatir's soil and trees and the atmosphere. So what is the rate? The organic carbon sequestration rate measured as the average between the carbon stock counting and the tower method was 550 grams of CO2 per square meter per year. And that's the average of the EC and carbon stock measurement. And it's comparable to the value you get in temperate climates. So if you now take these rates from Yatir, and if you make the assumption that Yatir semi-arid forest is representative of the global semi-arid area, it's a little step that just to get what you call a rough ballpark idea. Then the organic rate extrapolates to 3 billion tons of carbon dioxide per year after future global forestation. Why did we choose 20% and not 100%? Of course, because there are problems of finding the right site that has a reasonable amount of water, and another effect that I'll discuss which is the albedo effect. The albedo effect is that when you started, you just had the ground, and then you have good albedo. You have good reflection of the sunlight back to space. And then you go and you plant a forest, and it has nice green leaves, and it's darker, and it absorbs the sunlight. So you actually, because of you planted the forest, you have less reflection, and so you don't completely gain. You gain, but in reducing the temperature, because you're removing carbon dioxide from the atmosphere, but you lose because the albedo has decreased. So you have to choose the right areas where the slope of the land is away from the sun. So we had a reason why we talked about 20%. So I'm showing here now the chemical. How am I doing with time? I'm okay. We have the equations that show carbonate precipitation. So you see the equation 1, the soil carbon, the carbon dioxide exhaled by the tree roots during its usual living process combines with soil water. It makes the carbonic acid. It decomposes to H+ and the bicarbonate ion. And then that H+ can decompose limestone that's in the soil. That's equation 2. And it can make more bicarbonate. And equation 3 is the sequestration equation, that calcium in the soil that came either from equation 2 or that came by wind or other methods of blowing. And when I say calcium, I mean other elements, magnesium, anything that will combine with bicarbonate to form a salt. So it combines with the bicarbonate and it precipitates calcium carbonate over here. And then there's a problem that you can say that it releases CO2. In this process, for every 2 moles of bicarbonate, 1 mole is released, so you're not gaining very much. But this is only if you look at what happens near the surface. In semi-arid areas, the roots go very deep. They can go down to 20 meters because the tree is looking hard for water, and therefore this process takes place not near the surface, and the CO2 that is released and exhaled by the tree roots, it doesn't. Most of it stays in the soil in high pressure. Some of it gets out to the atmosphere, but it's a difficult process of diffusion. So therefore, you end up with sequestration. And besides, you can also get sequestration by using silicate rocks. And with silicate rocks, there is no release of carbon dioxide, even near the surface. It's just complete sequestration. So equation 3 implies no net sequestration, but our isotopic data show net sequestration because most CO2 from equation 3 does not return to the atmosphere, and many other cations contribute to equation 3. So now we also did isotopic measurements to make sure that the calcite that is precipitated in the soil, it really originated from the atmosphere. And there were two types. The one on the right shows that we did soil cores, and if you do a soil core, you look at the you take samples of soil down to in this case 14 meters. So as a function of depth, you take the soil and you extract by vacuum dehydration, you extract water, and then you look at the concentration in the water of the bicarbonate ion. The interesting thing is that as you go as a function of depth, the concentration of the bicarbonate in the water decreases. Why is it decreasing? Because as the water percolates down, part of the bicarbonate is lost as it precipitates and makes the salt, the calcite salt. So that's why the figure on the left shows the decrease of dissolved inorganic carbon. The dissolved inorganic carbon is mainly the bicarbonate. And as you go down in depth, the concentration of bicarbonate decreases. And similarly on the right, the concentration of carbon-14 isotope, you take that liquid and you extract the carbon, and then you do accelerated mass spectrometry and you measure the percent of carbon-14, and you can see that the amount of carbon-14 as a function of depth is decreasing. So near the surface it was high, and lower it's lower, and the only source of carbon-14 is in the atmosphere, atmospheric carbon-14. So what is our isotopic evidence for carbon sequestration? One, the atmosphere is the sole source of carbon-14 introduced into the unsaturated zone, dissolved inorganic carbon as C14O2, and then pedogenic solid in the unsaturated zone incorporates the carbon-14 as this dissolved inorganic carbon exchanges with relic limestone as the rainfall flows down. So we measure the decrease of bicarbonate as a function of depth. Now, how do we translate that to time? We translate it by time because in Yatir forest, by a separate measurement of using tritium as a tracer, because part of the rainwater that falls is not H2O, but it's HTO. And then using tritium as a tracer, you can look and find the tritium content in the percolating water as a function of depth. And then we were able to determine that the percolation rate is 11 centimeters per year, so that you were able to translate the decrease of bicarbonate ion as a function of depth into the decrease of bicarbonate ion as a function of time. So my third point here is atmospheric CO2 is tagged by radiocarbon, which is incorporated into the pedogenic carbonate, because we also look at the carbon-14 content of solid modules that are extracted. So this was not previously observed because we were only able to do it by accelerated mass spectrometry. And as far as we also measured the carbon-13 isotope composition, the ratio of carbon-13 to carbon-12, which is usually denoted by this delta carbon-13 C symbol. And when the carbon-13 is taken in as CO2, C13O2, it's taken in through the leaves, and it's taken in with a certain isotopic fraction. But as it goes through the tree, it's fractionated, and the heavy isotope doesn't get exhaled as easily as the light isotope. So we can see that the delta carbon-13 at the higher part of the soil core is minus 26 parts per thousand. And then as it goes, as we go deeper as a function of depth, because there is an interchange between the solid and the dissolved inorganic carbon, and then eventually it finds an intermediate value between delta carbon-13 that was released from the roots and the value in limestone. So the carbon-13 and carbon-14 isotope measurements demonstrate the atmospheric origin of the carbon dioxide that we see in the soil, the carbon dioxide that is sequestered. So now what about global extrapolation? So we consider a sediment volume of 1 square kilometer and 6 meters of depth. This is a rough estimate of the average depth in which the tree's roots will be active over semi-arid area of the planet. Some trees in semi-arid areas go down even to 20 meters. But 6 is a rough estimate of the average, and this would end up having 132 tons of CO2 per year per square kilometer. And so if you extrapolate this rate to 20% of the 27 million square kilometers of global semi-arid area, you end up with an estimate of 1 billion tons of inorganic carbon per year. And then we had the organic estimate, which was 3 billion. So roughly 4 billion based on this assumption. And it's at the moment, it's a guesstimate, not even an estimate, because we only have one measurement. And what about who's going to pay for all this stuff? Who's going to plant all these billions of trees all over the planet? Not the oil companies, but so it a little bit depends on whether the governments make regulations that impose penalties on polluters. Now, if they make these penalties and then demand that polluters buy carbon credits, then to offset the problems that they're creating, then the price of a carbon credit would go up. At the moment, without government regulations, you have polluters that will pollute, and they don't give a damn, and they're not gonna buy carbon credits, and the market price is too low. But as an example, 6.2 billion tons emission allowances and offsets were traded in 2015 that had a value of 48 billion euro. So the 4 billion tons that I was talking about per year at this rate would be worth 30 billion euro per year, and then everything would be fine. But the carbon credit markets have a funny way of operating. They only want to accept and offer credit certificates for people that make new sequestration. So if I go to the Yatir forest and it's been offsetting, it's been sequestering over the past 50 years, then they say, well, we won't pay for that because you have to do something new. So the only way I can get money out of the Yatir forest is to burn it down. And if I burn it down and then plant it again, then they will pay. But at this moment, until the rules are changed, we can only expect credits for new forests. But that's not a problem either, because there's a hell of a lot of land out there that has nothing on it except herding and grazing and not very useful economic activity. So carbon sequestration. Despite low precipitation, Yatir is productive, only 28 centimeters per year of rain. It stores organic and inorganic carbon relatively effectively without irrigation or fertilization. It has inorganic sequestration as the calcite, which is good for millennia. It has organic centuries, that's good for centuries. I mean, the trees live for 100 years and then they might fall and decompose. So a tree is good for, I don't know, 150 years. The inorganic is good for more, but you should always be planting new trees. So now it's a question of, can the forests live? Many rainfall deficient semi-arid areas often overlie groundwater reserves of fossil water that can be exploited. I give examples of the Nubian sandstone aquifer, the milk aquifer, the Great Artesian aquifer in Australia. So if you take, for example, Saudi Arabia had a giant fossil aquifer. I call it fossil aquifer because the water under the Saudi Arabian desert, it entered that aquifer at a different climate period when there were rains. And so it's not being recharged. So if you use that water and you keep using it, then you empty the aquifer. I mean, then you can have what they have in Las Vegas. You empty the water under Las Vegas, and then the land begins to sink. So you have to be a little bit careful. But they, in Saudi Arabia, they decided that they would use that water to grow agriculture, watermelon. So they were using it up, and they weren't putting it back. But they have a lot of oil money, so it wasn't a problem. They went to Arizona and they bought a huge land in Arizona, and now they were pumping water out of Arizona. But this method is not what you call sustainable. So that's another reason why we say 20% of the semi-arid forests, because we want to go to areas that have aquifers, fossil aquifers under it, that we can start the planting of the forest, and we can try to take care of the recharge. The recharge would require making desalinization plants. And besides, trees, as opposed to crops, they take about 3 times less water than crops. So if you go to a fossil aquifer and you do trees, grow trees there, then it's a better idea than using up the water to grow croplands. So anyway, as I said, we extrapolate the Yatir rates to 20% of the global semi-arid areas, and we get a global sequestration rate of 4 billion tons of carbon dioxide per year. So our estimate demonstrates the global potential, the need for further measurements, and the need to begin implementing a global land management policy of widespread tree planting in semi-arid areas. And this is a map from the GUM database, where they looked all over the planet and they estimated where there are sedimentary areas, and the soil is sediment. They looked only at the surface, but they found that porous sediments cover about 60% of the global semi-arid area. And then it's an assumption that there will be also sediments underneath that kind of area. If the top is porous, then there's more likely that underneath is porous. And then our 20% estimate is also based on the idea that 1/3 of this land has sedimentary rocks, soil underneath. And of course, if you want an aquifer and you want water underground, it'll only flow and be able to be extracted if the soil is sedimentary and not solid basalt. So this is a positive sign that it's logical to find fossil aquifers under many semi-arid areas. So what is the advantages of carbon sequestration in semi-arid forests? Extensive thickness of the unsaturated zone compared to temperate regions, therefore greater active volume for inorganic sequestration. The low rainfall precludes dissolving the calcite, and Yatir receives only 28 centimeters per year of rainfall. It's still functioning, even though it's the world's driest. It's still a healthy forest. And semi-arid forestation does not reduce food supply by decreasing productive temperate region agricultural land. And the organic net economic ecosystem production is comparable to the NEP in temperate climates. So the fact that you're doing it in semi-arid is you're not losing very much. And it can provide steady employment in economically depressed areas instead of marginal herding and agriculture. And the forests can also produce useful products, lumber, charcoal, carbon credits, and a very valuable product indeed also is oxygen that the forests make. Nobody wants to pay for Brazil to make oxygen, but we all need it. So as a summary, global extrapolation yields annual semi-arid sequestration rate of 4 billion tons per year for organic plus inorganic, which is a respectable 20% of the rate of atmospheric CO2 increase. The inorganic carbon is sequestered very long-term, the organic for something like 150 years, and the forests may generate valuable annual carbon reduction credits. And we need more data to better characterize the potential global sequestration rate. The fact that we make these estimates based on one forest and not the whole forest, but a little plot is a little bit not so good. And we should have more data, but to have more data, we need people who are interested and are willing to help. It's not so easy to plant billions of trees. Now you can do it a little bit by drones and put seeds in the drones, and then you can spread them over mountaintops or whatever. But to go with a shovel would be a little bit more difficult. So I thank you for your attention, and I have one last slide that summarizes the whole seminar. And that's here it is. Plant more trees.
Thank you, Mark.
Okay.
I hope this works. Yeah. So we can kick off the Q&A here. And if anyone has questions, please raise your hand. Otherwise, Becky is in charge of the chat. And Anna, please put questions in the chat or say that you have questions so that we can let you unmute. So does anyone have questions here? Yeah, John.
Yeah, thank you very much for the talk. I don't really have much in this area, but it's interesting to hear. But I was just wondering, when you're reforesting, planting these forests, I've heard all the issues of like if you're planting the same trees, monocultures, more prone to disease, possibly less biodiversity. I was just wondering what you think the practicalities with the ease of just reforesting an area, changing the whole.
Well, it should not be monoculture. You should worry about biodiversity, and you should have different varieties. So if one gets sick, the whole forest doesn't go kaput. But there is a problem of starting the forest. Like some trees, like bamboo, they grow faster than other trees. So if you're starting from zero, then you should choose the trees that grow fast. In the case of Yatir, it started as pine, but as I said, 4 million trees were planted over the years, over 50 years, and the Jewish National Fund foresters are changing it all the time and making it more biodiverse.
So do you think these, if it's done well, it can be as effective at sequestering carbon as a natural forest elsewhere than just a man-made one?
It can be done very well, yes. In semi-arid, if this is representative, to the extent that Yatir is representative of the global semi-arid region, then our estimates are good. To know, we should take measurements at 5 semi-arid areas in 5 different countries and look at an average. But that my colleague Joel and I, who have been doing this work, we're near 80 years old, so we're leaving it to you because it takes time for the tree to grow. So it's up to you.
Thank you very much.
Thank you so much. I know there's a difference between the sequestration rates of young trees versus old trees. And I was just wondering, because it was planted about 50 years ago, did you see that in the data? Did you see that difference?
That's very interesting. I don't know how much different it is, but the data were taken 10 years ago and the forest is 50 years old. So I don't think we would have been sensitive to that. Where somebody was here. Okay, rotating.
Atmospheric, and where else would it be coming from?
Well, suppose you have just calcite rocks in the ground, then you can have rainwater coming in, and it could so CO2 and rainwater can make carbonic acid, can make bicarbonate. The bicarbonate could combine with the calcium in the rocks, and that has nothing to do with the rocks have been there for maybe millions of years. So we want to show that the calcite that we precipitated, we want to show that it started in the atmosphere.
What was the reason to plant this forest like 50 years ago? What was the decision making?
Sure.
And what is the technology that you use to plant the forest? Considering it is a very arid zone, I think it is quite difficult to grow trees from the seed.
Yes, it doesn't work well from the seeds. Well, first of all, why did the forest get planted? Unlike the UK, Israel is a country that is independent now for 75 years. Okay, so starting in 48, then you had some organizations like the Jewish National Fund that decided that it was their job to relive the country. So it was part of the will to have a country. You know, you have your Sherwood forest, you don't have to plant it, and we have nothing, so you have to plant it. As far as technology, there's a company that I've been in touch with that has a patented cocoon technology. So the cocoon, because if you just plant the seed in semi-arid area, the probability that it'll make it through the first year is not so good. So in the cocoon technology, but that's more labor intensive. You basically have a container that has water in it with the tree, and it's enough to get the tree through the first year. Then if it gets through the first year, then it's probability of carrying on is higher. So the trouble, it works. They demonstrated that it works in semi-arid areas. It's a company in the Netherlands. But to do it is more labor intensive and more expensive. It would be nice just to drop seeds from a drone, but I think that won't work. Or they may start with a limb, a seedling, that not necessarily a seed. You know, they have nurseries where they can cut a branch and.
What is the decision made about what kind of species should be? Because we can see the
Well, the logical species would be to choose a species that's native to the area, because those are the species that figured out over millions of years how to survive. If you bring something from another area, well, it probably will do less good.
So you mentioned that there's more factors than just CO2 to the effects that forests have on climate. So did you consider any of those in your calculations? So basically, did you look at net forcing or just CO2?
Well, I talked about net forcing in terms of the problem of albedo, so which is a negative forcing. I'm not sure. You have an answer to that?
No, not really. They have been making a whole bunch of different types of measurements on the radiation input and export, how the forest may heat actually or cool. There's a debate on that where Rafat is studying. So we're not going to get in. We just wanted to measure how much it was sequestered, not the heating is what you want.
No, I was just wondering, like, if you had looked into what effect.
Well, suppose you wanted to have the forest in the temperate zone, and then you needed to add fertilizer, and then you have fertilizer runoff that badly affects the local water supply. If you do it in a semi-arid area, you're not interfering so much with the local population, that nobody lives there. Yes, absolutely. The albedo is a problem, but even the albedo effect is a problem of global warming. But the extra CO2 that is released by fossil fuels, it's not only doing warming, it's making ocean acidification. I mean, 100 of the carbon dioxide released by fossil fuels, okay, maybe 40% goes to the atmosphere, but the other 60% goes into the ocean and the soil. So even if we don't win 100% on cooling the planet, you can't just acidify the ocean and kill all the corals and fish. I mean, so you should anyway proceed.
Silwood Park campus, and we have a question.
Hello. Hi, Murray. That was really interesting, very informative. I've learned a lot. One thing I was wondering about was so maybe I missed this, but you didn't have any emissions estimates, especially emissions from microbial contributions. Is this, what's your, how much do you know about microbial contributions, and how much do they vary across space? Because there's a lot of discussion about the thermal sensitivity of primary production being different from the thermal sensitivity of
Totally understand.
microbial respiration, which seems to be more sensitive.
Can you repeat the question? I'm sorry.
Sorry,
No,
maybe it's better.
It's the sound level.
Try again. Is it better now?
Yeah, it's better now. Thank you.
Okay, thank you. No, so I was wondering about microbial contributions and the thermal sensitivity of microbial respiration versus plant respiration, which in my understanding is different. Microbial thermal sensitivity is steeper than plant thermal sensitivity for both photosynthesis and respiration. So with warming and also across geographical gradients, I guess you would expect a disproportionate increase in respiration from microbes. I was wondering what your view is of all of that within the context of the systems you've been studying.
Well, part of the sequestration is not only the CO2 that is exhaled by the roots, but also the decomposition of roots and organic material in the soil that gives an extra contribution to the CO2 level of the carbon. Do you have something on that?
No, it's just that we started off at very, very low organic level in the soil. That's one reason why the trees were planted, is that the country suffered tremendously from the soil runoff. These were bare hills. There, you were down to the bedrock, which was limestone. So you had to put in not only trees, but first you had to put in at least 30 centimeters of soil. And this soil was very low in organics, so we had very low microbial activity. In fact, in the very beginning, they had to use sewage water, sort of like fertilizer, to bring in the microbes. So this problem we haven't really dealt with, how much, because we're trying to bring in the microbes. And we should show pictures, unfortunately we don't have it, of what the area looked like before and after.
That's a good idea.
And what we showed trees, but this was bare hills. Much of the problem was that you had the soil runoff, and you also had the Ottomans put in a railroad, north-south, a railroad, and they used wood burning trains. So they cut down the forest. And on top of that, they had a very progressive sultan. The sultan said, well, there's a lot of large latifundia for very rich people, and they have a lot of area, a lot of non-fruit bearing trees, as opposed to little farms that are subsistence that use, palm trees, and they use it for food. So how do you equate a big area with luxury living with a lot of trees that are not productive agriculturally to a farm who works hard and he just produces his bare minimum? So he said all non-fruit bearing trees should be taxed. You know what this did? They immediately went into the forest, the rich people, and they chopped it down. which caused, this is a true thing. So this, and this led to much increased, soil runoff, which eventually carried out, which led to, the denudation of large percentages of the country, of any soil. So it's not just planting the trees, but first you had to put in the base, which was the soil, and then you planted the trees. So, yeah, there was a lot of problems going on. And one of them is that you didn't have any soil, a normal soil flora with the microbes that I guess you were talking about. So we're trying to still bring this back in, and it is physically intensive because they're planting the trees not by seeds, but by seedlings. And hopefully, maybe it'll help cool the climate locally and will bring in more rainfall, which is problematic still. So that's what I have to say. Any other question? Murray?
No,
Okay, so I think we can wrap up now. It's 10:05. So thank you, Mari, for staying with us a bit longer. Thank you, everyone, for joining. The next seminar will be on the 28th of June, and we'll have Guy Owen, who's the director of the Cabo Institute for the Environment at the University of Bristol, and he'll be talking about water and sanitation systems in low and middle income countries and how they can be adapted to the for the future in a climate change. So for anyone who did not have a chance to ask questions to Murray or Joel, I'm pretty sure they're happy to chat about it while we have the refreshment in the networking session afterwards right now. So thanks everyone in Fieldwood and everyone online for staying with us, and everyone here, we can now just have a couple of drinks and a chat. So thank you everyone for joining, and thank you again, Murray.
yes, and
for
thank
the
you. It was a
wonderful
pleasure. Thank you. What, did I survive it?